Uh, Good afternoon. I'm Michael Nababi with AZ Water, and our presentation is going to be by David Axworthy. He is a principal with Northwest Hydraulic Consultants, over 30 years of experience in hydraulic transient analysis of pipelines, pump stations, regulating valves, well fields, and hydrostatic, hydroelectric facilities. Welcome, David. We look forward to your presentation.
Thanks for that kind introduction, Michael. I appreciate the opportunity that AZ Water is giving me to speak with you today on the importance of surge control for water distribution systems and pumping systems. I'll start the presentation with a brief overview of the webinar today. First off, we're going to talk about the consequences of surge pressures and distribution systems, particularly those caused by pumps. We'll look at a few of the examples of pump-induced events that create surges in distribution systems. We'll talk briefly about the various surge control design criteria that we use in order to determine whether or not surge protection is necessary for a pump station and distribution system. We'll spend most of the time talking about surge control strategies, and I'll demonstrate the effectiveness of some of those with movies. And we'll wrap things up with some question and answers at the end. Most of us are very familiar with high positive pressures that can be created during a surge event of any kind. Those positive pressures often can crack a pipe. Even in worst case scenarios, they can rupture a pipe, as shown in the photo on the right here. But what's less realized or recognized by most engineers is that large magnitude negative pressures also are of primary concern when it comes to surges and distribution systems. Large negative pressures have the potential to collapse pipes, damage linings, damage joints and seals. And if there are any leaks in potable water systems, then the negative pressures that are applied to a leak location could create a potential for intrusion of contaminated water. So you might have pathogens being introduced into your treated water system during a negative pressure event. Other consequences of pressure surges in distribution systems include that of air and vacuum valve slam. Combination air valves, regular air and vacuum valves, are usually installed on distribution system pipelines in order to provide for filling and draining of the pipelines, as well as for releasing any air that comes out of solution during the operation of the pipelines. But they're not really there for surge control. They're not really designed for surge control. So one of the concerns, or one of the consequences of surge events is that when we have a pump power failure, for example, the pressure drops in a pipeline, it opens up combination air valves. They allow air into the pipeline. Then at some point later in the surge event, the pipeline repressurizes due to maybe a reflected pressure wave. And that causes the water to flow back up into the air valves that had previously opened and allowed air into the pipeline. And the force by which the water, velocity by which the water enters the combination air valve can be quite high and cause the valve float to slam closed. The slamming of the valve float can damage the float. It can also damage the valve seal that is between the top of the valve and the float itself. The end result is the valves end up leaking and possibly flooding out properties downhill from where a vacuum valve is located. Another consequence of pressure surges involves the change in the flow direction within the pipeline. If there's a pump power failure, the flow will be in the forward direction, but eventually will reverse and flow back towards the pumps. If the pumps are equipped with check valves and those check valves don't close prior to the flow reversing, then the reverse flow may slam close those check valves, and we get what we commonly refer to as check valve slam. That can often damage the valve seats. It can create additional adverse high pressure surges. And it obviously makes a large audible sound, which is discomforting to the operators. If the valve seats are damaged in this way, then the check valves are likely to leak and can allow water from the high pressure side back to the low pressure side of the pumps, which is definitely undesirable. So there's lots of consequences within the pipe itself and within the infrastructure itself that can be damaged or significantly compromised by a surge event. But surge events also have the potential to damage infrastructure that's above the pipe and to the side of the pipe. And just to give you a feel for just how devastating a surge event can be, I wanted to play this little video from 1997, which is the aftermath of a break that occurred as a result of a power outage in a system here in California.
Simi Valley residents are back in their homes now after a ruptured water main forced them to evacuate, but repair crews continue to work around the clock to repair the damage.
This looks like a raging river, but it's Madera Road in Simi Valley. It was just before 5 o'clock Saturday when a water main burst, forcing a flood of water to pour into the street.
My wife heard it. She said it sounded like a pop, kind of like a loud light bulb going off. And then she heard screaming from across the street.
Across the street is a shopping center which was filled with people at the time the pipe burst. Suddenly, they were cut off by water gushing out at 20,000 gallons per minute. A half-mile stretch of Madera Road was quickly flooded, and with the water rapidly rising, nearby residents were told to evacuate.
You need to get away from the wall and go to the front of your house now.
It was just a raging torrent. I mean, it was like, raging.
Crews have been working non-stop to repair the damage. Now that the water has receded, you can get an idea of the immense force the water carried. Huge chunks of asphalt were ripped from the street and thrown to the sidewalk. The problem started a few days ago when a contractor working on the nearby Wood Ranch development cracked the water main. The valve under Madera Road was closed for repairs, but a power outage on Saturday created a giant pressure surge. When the water hit that closed valve, it couldn't contain the pressure.
So needless to say, there's very good reasons for attenuating surges to acceptable levels in pipelines. Turning from the consequences of surges to the events that create pressure surges in pipelines. Today, since this presentation is mostly about pump systems, I'm going to focus primarily on pump power failure. I'm also going to talk a little bit about pump shutdown under controlled power conditions, as well as pump startup, because they can all create surges in distribution systems. Keep in mind that there's lots of other devices in distribution systems, those being valves that might close or open or modulate. Pipeline ruptures can even cause surges in distribution systems. Increasingly, we're seeing turbines installed in parallel with PRV stations and flow reduction stations to generate electricity. And load rejection or load acceptance at those turbines can also introduce surges into distribution systems. This video playing on the right-hand side here is simply just a three-dimensional view of the results of a pump power failure or shutdown scenario. In order to, we'll start with pump power failure, but in order to demonstrate just what happens during a pump power failure, I set up a very simple example system that we're going to use as part in this webinar to demonstrate both the surge events and also the effectiveness of surge protection. So this is a very simple system. It's a pump station on the left. It's pumping up to a tank on the right through a pipeline, which is shown in green here. The pipeline is about 6,800 feet in length, 12-inch PVC. It's initially operating at about 1,400 GPM, which is about 4 feet per second in the pipe. Take note of the dark blue line. That's the steady state hydraulic grade line from the pump station to the pipeline, to the tank. And as you can see, it's gradually sloping to show that there's friction loss in the pipeline between the pump and the tank. When a pump power failure occurs, what we get is a rapid drop in the rotational speed of the pump. And that is in part a function of the polar moment of inertia, or WR squared as it's called. This creates a sudden and rapid reduction in flow and head at the pump. And the pressure drop that occurs in the pipeline as a result of this pump power failure is proportional to the reduction in the flow velocity within the pipeline itself. This equation here that I've got is just for illustrative purposes because it's very approximate and doesn't actually account for the effects of friction. But it does give you a general feel for what the change in pressure would be based on the change in velocity. And it's called the Joukowsky equation. It basically says that the pressure head is proportional to the acoustic wave speed. In this particular pipeline, we're talking about a PVC pipe. So the acoustic wave speed would be about 1,300 to 1,500 feet per second. And that just represents the speed at which the pressure wave is traveling from the pump station to the tank. So you can imagine in a pipeline that's 6,800 feet, it's only going to take about 3 to 5 seconds for that pressure wave to traverse from the pump station to the tank. The rest of the equation involves the gravitational acceleration and then, of course, the change in velocity that's created by the pump rundown on power failure. What's important to note here is that the pressure drop creates a parabolic shaped pressure wave, and that propagates from the pump station into the pipeline. If you move forward a little bit in time after the power failure, you'll see that that pressure wave continues to drop at the pump station and also continues to propagate down the pipeline. It's not quite intersecting the pipeline profile yet, but it's getting very close. We move forward a little bit more in time, the pressure wave continues to propagate towards our tank, and it drops the hydraulic grade line low enough that it opens that first air valve that's on at a local high point on the pipeline. And the air valves are just shown as these small triangles. Moving forward again in time, what we can see is the hydraulic grade line, or the pressure wave, continues to propagate towards the pump station. It now has dropped low enough that it's opened both of the air valves on the pipeline. And between the air valves, since we don't have anything to hold the hydraulic grade line up, it continues to drop below the elevation profile of the pipeline. In fact, in this particular case, it drops low enough to reach what we call vapor pressure. And vapor pressure is essentially absolute zero pressure. At that point, the water itself will boil and vapor cavities will be created as a result. If those vapor cavities get quite large, they can actually separate the water column. And if we think of the water in the pipeline as one large column of water, anywhere where you get a vapor cavity forming, it has the potential to push apart the water and even maybe separate the water column into two separate columns. That's commonly called water column separation, and many of you may have heard of that in the past. Now, the vapor pressure is essentially like a constant head boundary. The pressure can't drop any lower than vapor pressure in the pipeline. So when the hydraulic grade line reaches the vapor pressure boundary, it essentially wants to reflect off of that and reflect back towards the pump station, which it's doing in this particular slide, which is a few seconds further into the simulation. When the reflection takes place, it will collapse those vapor cavities that formed at vapor pressure back into solution. So they'll collapse much like a cavitation on an outboard motor. And at the same time, the water columns that had been previously separated by this vapor cavity will come back together. And the best way to, or a good analogy of the vapor or the water columns coming back together would be two locomotives on the same railroad track, each heading towards each other. When those locomotives eventually impact and crash into each other, they're going to create a high positive energy. And the same thing will happen when the water columns come back together. They'll crash into each other and create a very high positive pressure. And that's what the next slide shows. we get a very high positive pressure spike whenever we have a cavity collapse and a water column rejoinder taking place. Now, the magnitude of these positive pressure spikes is impossible to calculate with any accuracy using modern numerical models and transient software. But we know from laboratory experiments that these pressures are well above 300 psi. And in most water distribution systems, that's going to be a pressure rating high enough, or a pressure high enough to exceed your pressure rating. And if it's added to the steady state pressure, probably well above your maximum allowable based on your surge capacity. So many good reasons to avoid vapor cavity collapse in pipelines following pump power failure. And this is primarily what we see in most water distribution systems when a pump loses power. Now, I want to just show you a simulation that sort of puts all these slides together so you'll better understand just how this wave both is created and propagates through the system. So that's what I'm going to show here. But before I start the simulation, I just wanted to define what we're looking at here. The pipeline is shown, the pipeline elevation profile is shown in red. The dark blue line is the initial steady, or the instantaneous steady state, instantaneous hydraulic grade line rather, during the simulation. The steady state hydraulic grade line is right up beneath that, and it's shown as a dashed green line, which you'll see in a minute. The maximum and minimum hydraulic grade line during the simulation will be shown as a yellow and a light blue line, respectively. So let's start that simulation again. What you'll see on the left is the development of the pressure wave, that parabolic pressure wave that creates a drop in pressure in the pipeline. Eventually drops low enough to open both of the air valves. Then we get a reflection coming off the vapor pressure between the air valves, and then a repressurizing of the pipeline. And it's that point that the vapor cavities would collapse and produce those large spikes. Now, I haven't tried to calculate those spikes with the numerical model because, like I mentioned before, the numerical models don't accurately calculate those, but it's enough to determine that we do have vapor pressure that we know we have to eliminate that from the system if we want to properly protect this pipeline. So that gives you a feel for what happens during a pump power failure in a typical distribution system. After you've determined that you have a surge problem, then you want to turn to the surge control design criteria to determine what needs to be installed for surge control and whether in fact you need surge control. Here are some of the design criteria that we use to determine whether or not surge control is necessary. We look at the results of the analysis and we say if the predicted maximum pressures are exceeding the pressure rating plus the surge allowance of the pipe, then surge control is going to be necessary, and we need to start thinking about what kind of surge devices we want to put on this system. We also look at the predicted minimum pressure. Does it drop low enough to reach vapor pressure like it did in the previous example? Well, if it does, then for sure we need to look at some surge control in order to stop that from taking place. Now, in some cases, the hydraulic grade line may drop, but not low enough to create vapor pressure. But it still might create some negative pressures and put the pipe under a negative pressure condition. In situations like that, we also want to control those negative pressures to acceptable limits for the pipe material. And that's going to vary with the pipe material and even perhaps the project itself. In treated water systems like what we're talking about today, ideally, we'd like to completely eliminate negative pressures during a surge event so we don't have any risk of pathogen intrusion. But there will be situations where it's just practically impossible to do that, and you still have to allow for some negative pressures. And in those cases, we revert back to the material to determine just what's acceptable and what's not. Another question we ask is, are any of the combination air valves in the system predicted to open and slam closed? If they are, then yes, we need to look at surge control measures in order to prevent that from taking place. And we'll talk a little bit more about that later. Some other criteria we look at is we check the air valve pressure differential that occurs when an air valve does open during a surge event to make sure it's within the manufacturer's acceptable limit for the valve. We don't want the valve to be overtaxed in terms of its vacuum capacity. Otherwise, it won't provide the necessary vacuum relief. So checking that's very important. We check all of the tanks. They could be surge tanks, standpipes, reservoirs, and other storage tanks to make sure that proper water seal is being maintained during the transient event. If it's not, then you're going to potentially drain the tank and introduce air into the pipeline, which may then start to travel down the pipeline. If that air gets trapped somewhere, it's going to suddenly stop the water column, and the water column is going to potentially create some additional adverse surges. In addition, if you have trapped air in your pipeline, it's going to make it difficult to restart your pumps once the power comes back. So preventing air from getting into the pipeline is definitely important, and surge control can help prevent that. The last item here is we check the velocities through any critical valves like pressure and surge relief valves, as well as inlet and outlets from surge tanks and other tanks and reservoirs and standpipes to make sure that they are within acceptable limits. If the velocities are exceeding the acceptable limits, then they may get into a choked flow condition, which would make them less effective and potentially not even effective. So need to make sure that those are within acceptable limits. So those are some of the surge control design criteria you should be using in order to determine what are your system needs surge control. So let's turn from that to what are some of the measures that we can look at in order to protect our system from adverse surges. One of the very best ways you can protect a system from adverse high pressures as well as adverse low pressures is with a pressurized surge tank, which is also called an air chamber or a pressurized vessel, sometimes a hydropneumatic tank if it's being used for demand duty as well. And these are basically pressurized tanks which contain a volume of water and a volume of either air or gas. Sometimes they have a bladder when they're a bit smaller than the one pictured here. And essentially, when you have a power failure, the flow comes out of the tank into the pipeline to make up for the flow that was previously being conveyed by the pump before a power failure. And that helps to attenuate the pressure wave that's created on power failure. Similarly, on a startup, the flow is going to go into this surge tank, and it's going to help to attenuate that upsurge that's created by starting up the pumps. Now, whenever you have a surge tank at a pump station, if you have check valves on those pumps, then they should be equipped with oil-controlled bottom buffers. And those are basically dash pots that are going to prevent any check valves from slamming closed. It's important to understand that when a surge tank is installed at a pump station, the flow reversal is going to take place much quicker than it will without a surge tank in place. And for that reason, check valve slam is much more of a concern. So adding controlled bottom buffers to those check valves usually takes care of that risk and makes for a safe operation of both the pumps, check valves, and the surge tank. Just to give you a feel for how effective a surge tank can be, what I did is I took our little example that we just looked at a few moments ago, and I added a surge tank to the pump station and re-ran that simulation for you. And you can see that the pressure drop wave that's created by the pumps with the surge tank in place is much more attenuated than it was in that earlier simulation where we didn't have any surge protection other than just the conventional air valves. In this particular simulation, I converted one of the air valves to what we call a controlled venting valve, which I'm going to talk about in a moment. And you can see here that our minimum negative or our minimum hydraulic grade line has dropped just a little bit below the pipeline, but it's mostly stayed positive throughout most of the pipeline. So much better performance than what we were getting without any surge protection. And the high pressures are not that much higher than the steady state. In general, you can see how the pressure wave is much slower in terms of its oscillation than it was without any surge protection. And that's another characteristic of a surge tank. It turns the transient from a fast transient into a slow surge, which is ideally what you're trying to accomplish with surge protection. Another surge control strategy or device that can be used with great effect to protect a pipeline in a pump power failure condition would be the installation of controlled venting vacuum relief valves. This photo just shows one example, and there are many different types of valves that are called controlled venting vacuum valves. Essentially, they allow a lot of air to get into the pipeline on a vacuum condition. Once that vacuum condition is alleviated and the pressure and the pipeline starts to repressurize, the air is essentially trapped in the pipe and in the valve body, and then very slowly released from the pipeline so that your air valve does not slam closed and damage the float or the seal, which might have otherwise led to leakage of the valve. So in order to protect our example pipeline from surges, what I did is I set up a strategy just using controlled venting vacuum valves solely. And so I installed I think about 7 or 8 on this pipeline, and reran our simulation. And you can see that the pressure drop wave is essentially the same in terms of the magnitude as it was without any surge control. But the difference is all these air valves open. They allow lots of air to get into the pipeline and control the negative pressures to what we would consider to be an acceptable limit for this particular pipeline. When the air is vented from the pipeline, it's vented very slowly, so we don't get any air valve slamming taking place, which could potentially create some very high positive pressures in the pipeline. One of the downsides, of course, of this sort of strategy is that there's a lot of maintenance involved in checking and maintaining all of these air valves on a yearly basis to make sure they're always in good working order. Another surge control device that's very effective is the Flywheel. A Flywheel is basically a large steel disc that or wheel that is installed usually between the pump and motor, and it increases the polar moment of inertia of the pump and motor combination. Like I said before, the polar moment of inertia has the the rotational speed of the pumps when they lose power run down in proportion to the polar moment of inertia. So if you can increase your polar moment of inertia of your pump and motor combination, then you can help to attenuate that pressure drop that's created on power failure. And so going and installing flywheels on our example pumps in their example system, rerunning the simulation, you can see exactly that by increasing the polar moment of inertia, we really attenuate that pressure drop wave that's created on power failure, hold up the pressure quite well, almost as well as the surge tank. And we only open one of the air valves on the pipeline as a result of that. One thing to keep in mind with flywheels, though, when you're sizing them, you're going to have to make sure they're sized sufficiently large to be able to control the maximum minimum pressures in the system to acceptable levels prior to closure of the check valve. After the check valves at the pumps close, the benefit of the flywheel disappears. It's gone because it's part of the pump, and the pump is disconnected at that point. So unlike a surge tank, which is always online both before and after the check valve closure, a flywheel is only going to be effective prior to check valve closure, but it can still work very well as long as it can be sized to give you that benefit prior to closing of the check valve. Now, a lot of manufacturers don't like flywheels and often void warranties on pumps and motors if they're installed, but when they can be installed, they can be very effective, and they're almost zero maintenance, which is a really great benefit of this type of measure. Another surge control measure that's very effective is the surge tower or standpipe. These can be installed either at a pump station or along the alignment of a pipe at maybe a local high point where you might otherwise have an air valve. They're really great at controlling both high and low pressures, much like a surge tank or a flywheel. Downsides is that they are open to the atmosphere, which is not ideal in a treated water system, but is certainly fine for a raw water system. And they will often be quite tall, particularly if they're installed at a pump station. But like this example shows, and I've installed one at the pump station in our little example for today, when they are installed, they are very, very effective at controlling the high and low pressures. As you can see here, the minimum hydraulic grade line and maximum hydraulic grade line don't drop that far above or below the steady state after power failure. One of the downsides is, like I said, they're very tall if they're at the pump station, and in this case would probably be impractical because it would be several hundred feet in height. But the concept is still applicable, and certainly it could have easily been installed at the high point of the pipeline, but we'd probably need other surge control at the pump station in addition to that. Something else to keep in mind when planning pipelines is that oversizing of the pipe diameter can be a surge protection strategy too. We talked a bit about how the change in pressure is proportional to the change in velocity in a pipeline. So returning to that equation, if we can somehow reduce the velocity, the initial steady state velocity in our pipeline by increasing the diameter, then any change in velocity that occurs, assuming the change in velocity is from the steady state to zero, for example, any change like that is going to result in a smaller change in pressure head, and therefore it's going to help to protect your pipeline in the event of something like a power failure or a pump startup. I went ahead to our example system, and I increased the diameter of that 12-inch pipe to a 36-inch pipe. That reduced the velocity of the pipe from 4 feet to 0.5 feet per second. And you can see here, it really made a big difference. The pump power failure, maximum minimum hydraulic grade lines are well within the acceptable limits for the pipeline. We only get a little bit of negative pressure at the downstream end. Of course, it's maybe not realistic to install a pipe that much larger, but something to keep in mind anyway. If you can go with a bigger pipe, that can help to at least partially attenuate your surges, and maybe means less surge control elsewhere on the pipeline. Obviously, in a wastewater system, this is probably not very practical because you would have to you would lose your potential to keep solids suspended if you were to drop your velocity to as low as half a foot per second. But it does have application in raw and treated water systems. Another planning consideration when designing pipelines for distribution systems is to look at the possibility of different alignments, particularly alignments that might allow for a lower elevation profile between the pump station and the tank. Although this will increase potentially the steady state pressure, may even result in some tunneling at times, it can have a really beneficial attribute of minimizing surge control for a system, particularly surge control that's trying to alleviate low pressures. To give you an example of what I mean, I adjusted the profile of the pipeline, for example, so that it takes a lower approach to the tank. And then I reran the simulation with exactly without any surge control other than just the two combination air valves that we had originally shown on the pipeline. You can see that by changing the pipeline profile, we eliminate a lot of the negative pressure from the pipeline. And so it certainly had some benefit there to considering other alternatives for alignments. Moving on to pressure and surge relief valves. Pressure and surge relief valves are really great at controlling high positive pressures in pipelines during surge events. However, they don't do anything for low pressures, so they're not going to be very beneficial if you're trying to just alleviate a low pressure problem. But sometimes we need both high pressure and low pressure control in a system following a pump power failure. And you can see in the previous example that I just showed with the change in the alignment, the positive pressures were quite high in that system. And just backing it up to show you there, when we have a high positive pressures developing, then we might want to put a pressure relief valve at the pump station in order to control those. So if we add a pressure relief valve, and a pressure relief valve will open quickly whenever the pressure exceeds the set point pressure for that valve, and then it'll close slowly in a controlled manner so it doesn't create any additional surges when it closes. So if we add a pressure relief valve to that same system that we had modified the pipeline profile, you'll be able to see that the pressure relief valve opens at the pump station, which is on the far left there, And it controls the maximum pressures to a lower limit than it would have otherwise been controlled to if we had not put in that pressure relief valve. Surge anticipating valves. Surge anticipating valves are popular with a lot of agencies, but they have to be used very, very carefully. They do have application and can be very effective, but it's often my experience that most people don't really understand how they work and where they should be applied. The purpose of a surge anticipating valve is to open very quickly on pump power failure. Sometimes there are other set points like a high and a low set point, which will also trigger it to open, but it's primarily used for pump power failure. After the valve fully opens, it will go and close in a slow manner. And the purpose of the valve, or at least ideally, is that it's there to reduce any high positive pressure wave that is reflected after a pump power failure. If we were to add a surge anticipating valve to our example system, what you would find is that it does in fact help with regard to high positive pressures. It controls the positive pressures quite well, and you'll see that in a moment. But what's important to note here is that by opening that pressure or surge anticipating valve right at the pump station on power failure, we actually created a larger pressure drop wave. And that's because we let a lot of the water out of the system, and that allowed the pressure at the pump station to drop faster and further than it would have if we hadn't even installed our surge anticipating valve. So we ended up with a lot more vapor pressure in the pipeline than we would have if we had not even installed that surge anticipating valve in the first place. What it is good for is controlling the high positive pressures, and you can see that here, but it's not going to eliminate that potential for vapor cavity collapse, which could create some very high positive pressure spikes that would not be controlled by the surge anticipating valve, because it's back at the pump station and the vapor pressure is being created and the spikes are being created in the pumps in the pipeline itself. So these have to be used with extreme caution, and I have used them from time to time in very specific situations, but they are not a surge control strategy that should be used without some significant analysis prior to selecting them as an appropriate device. It's very popular these days for large agencies to be looking at installing uninterruptible power supplies as well as battery backup systems to help in the event of a power outage. These are really great because the power just transfers immediately from the grid to these batteries, and you don't have a power loss to your pumps. However, they should not be considered to be a substitute for hydraulic surge protection. And that's because if you are, they will not provide hydraulic surge protection in the event that an operator, for example, was to activate an emergency stop of the pumps. In that case, you're into a regular pump power failure condition. That operator wants those pumps to be stopped, and they want them to be stopped as quickly as possible. They're not going to wait until the battery backup ramps down the pumps. Similarly, if you have a shaft break between your pump and motor, you're going to lose all drive, and your battery backup system is not going to help you in that situation either. You're going to be into a situation where you have a regular loss of power to your pumps. So these systems are great. I think they're a great addition to pump stations, but they are not a substitute for hydraulic surge protection. Turning from pump power failure to pump shutdown, the best way to start a pump is to start it, or to shut down a pump rather, sorry, is to use variable frequency drives and or pump control valves. These can be used to either ramp the speed of the pump down very slowly, or to reduce the flow that the pump is pumping and shut the pump flow off very slowly, and then trip the pumps behind the closed pump control valve. Either way, I just wanted to demonstrate how effective it can be with a shutdown in our example system. In this case, we used VFDs to ramp the pumps down in 100 seconds. You can see that the minimum hydraulic grade line isn't even dropping to the pipeline profile. and the maximum hydraulic grade lines barely getting above the steady state. So a really effective way of controlling surges under powered conditions in a pipeline is by using either a VFD, or similarly, you could get the same effect with a pump control valve. Turning from controlled shutdown to pump startup can also create surges in pipe and distribution systems. In this case, it's an upsurge wave that's created when the pumps are ramped up to speed. If we don't have VFDs or pump control valves on the pumps, then the pumps are going to come up to speed very quickly, almost instantly. And that's going to create a very sharp wave, upsurge wave, a very sharp fronted upsurge wave that is going to propagate out from the pump station towards our tank. Just to give you a feel for what an across the line sort of startup would look like, I performed one with our example system. And you can see that initial pressure wave that's created is very steep and very large in magnitude potentially. We want to attenuate that wave so that it's not as steep, nor is it as large in magnitude. And the best way is to, again, use the either the VFDs or the flow control or the pump control valves at the pumps. And to give you a feeling for just how much of a benefit they would be, I reran the simulation for a 60-second startup of the pumps, and you can see that the pressures are much more attenuated throughout the pipeline, and we don't get that very sharp fronted pressure wave being introduced to the pipeline, which otherwise would essentially shock the pipeline. We want to eliminate that or prevent that from happening on startup of the pumps. So what I'll do is I'll just conclude with a few remarks. You can probably see from this presentation that one of the best ways to control surges in pipelines is actually by combining numerous surge control devices. And we find this to be the most effective and the least cost strategy usually. Some examples might be to install a surge tank at a pump station with a couple of controlled venting vacuum relief valves on the pipeline just to help hold up the hydraulic grade line and in the event of a pump power failure. And also that would help to minimize the size of the surge tank at the pump station. If a surge tank is not desirable, then you can certainly go with numerous controlled venting vacuum relief valves on the pipeline itself, but you might want to pair that with a pressure relief valve at the pump station in order to control the high positive pressures during a pump power failure with the pressure relief valve. Flywheels are a really great alternative, as we showed, and combining those with maybe a standpipe at a high point would be a really great surge control strategy, and we've certainly used that on a few occasions. Keep in mind that looking at different pipeline material types can also be an advantage. As I showed in the pressure or the Joukowsky equation, the pressure the changes or surge pressures rather are going to be a function of the acoustic wave speed, and the acoustic wave speed is a reflection of how rigid or flexible a pipe is. Now, don't make the assumption that a flexible pipe is always going to be the best when it comes to surge protection because it has a lower acoustic wave speed. It's not always the case. So both need to be evaluated from in a surge analysis to make sure that one is not preferable over the other. Because I have had cases where a rigid pipe is actually better than a flexible pipe. So it's not a rule of thumb that a PVC or HDPE pipe is going to be better for surge protection. And we haven't talked much about booster pump stations, but in a lot of distribution systems, we boost from one pressure zone to the other. In a situation like that, it's often useful to have a bypass with a check valve so we can make use of some of that high positive pressure we've got on the suction side from the suction pressure zone, bleed it through to the discharge side during a pump power failure to help control that pressure drop wave that is created on a power failure. And obviously, using VFDs and/or pump control valves at the pump station for startup and shutdown is essential to maintaining or preventing surges from developing during powered conditions. Finally, many of the surge control options, or there are many surge control options available. They all need to be evaluated before selecting a preferred controlled strategy. That doesn't necessarily mean they all have to be analyzed in a quantitative manner, but they should be at least looked at in a qualitative manner to see whether they have any value before you settle on a surge control strategy. It's very important to have good suppliers who have experience with proper installation of surge control devices. Someone who's never installed a surge tank before is probably not going to be a good choice for your surge tank supplier. And of course, like everything in a distribution system, it's very important to maintain the surge control devices, check on them each year. Particularly in treated water systems, a year is probably sufficient. And that's because they need to be functional when you have a transient event, and you can't predict when you're going to have your transient event. So you must, it's very important to have a good maintenance program in place that ensures that the surge control is always there when you need it. And with that, I'll conclude the presentation and open things up for any questions that people might have.
David, can you hear me okay?
Yes, I can.
Can you kind of briefly go over the costs involved with any of these devices that you talked about, like controlled venting valve versus flywheel versus surge tower, stand pipe,
Right.
and VFD? What would be the cost range of these?
Unfortunately, the cost varies significantly with the system and the scale of the surge control. So it's not that easy to necessarily for me to give you costs right now. But what we typically do is we'll look at we'll develop a number of different strategies, and then we'll have each of those strategies costed for a particular project to find out what's going to be the most cost-effective method. And then we'll evaluate that cost versus what's the benefit of the surge control. Is it going to provide, is it one strategy much better than the other? And we'll also, you can't just look at the cost of installation. You need to look also at the cost of maintenance. Maintaining air valves, for example, is going to be a lot more expensive than maintaining a surge tank. So even though a surge tank is likely going to be significantly more expensive than using air valves, assuming you don't need a 50 or 100 air valves, then your surge tank might be a better longer term investment in that case. Similarly, a flywheel, you don't have any maintenance at all, but you might need to have a larger pump station to accommodate the flywheel between the pump and motors. And if that's the case, then you're going to be spending more capital at the design and construction stage, but you're going to benefit with a very low maintenance surge control device.
Mm-hmm. Awesome. If you could one more time explain how the bypass with check valve at booster pumping station works.
Sure. Well, when I demonstrated the pump power failure, you saw that the pressure dropped suddenly on the discharge side of the pumps. And that happens like almost instantly after loss of power. The reverse actually takes place on the suction side of the pumps if we're taking water from another pressure zone. So in other words, our booster pump station is not taking water from a tank or a clear well, like I was assuming in the example, but rather from another pressure zone. So you're going to get a pressure upsurge wave, which is the opposite of the pressure downsurge wave being created on the suction side. If that pressure upsurge wave actually exceeds the pressure on the discharge side of the pumps at some point during the surge event, which it frequently does, then you could make use of that higher pressure to bleed water from the suction to the discharge side of the pumps in order to help hold up that discharge pressure. And the way we would do that would be to install a bypass that's in parallel with the pumps. And we would equip it with a check valve, just like you said. And that check valve would allow for flow from the suction to the discharge side, but it would not allow flow to flow in the reverse. So when the pumps are normally operating, there would be no flow, but it would be an automatic bypass. There wouldn't be any active control. It would just automatically open when the suction pressure exceeds the discharge pressure. And that would in essence help to attenuate the pressure drop wave. Now, often you still need some other surge control in addition to that, but it might help to reduce, for example, the size of the surge tank that you might otherwise need on the discharge side if you can make use of some of that suction pressure. But it's not the case for every system. Every system's different, so it needs to be analyzed and designed to see whether it's even going to be effective or not. But when it is, it's great.
Yeah, thank you for explaining that. Appreciate that. Do we have any other questions?
I got one question for you, David.
Sure.
In your surge tank example, I guess, is larger surge tank always better to help mitigate both the high pressure and low pressure waves?
Well, it's not just about the volume of the tank. It's also about the volume of the air or gas that's within the tank. Generally, when you have a larger tank, you're probably gonna have a larger volume of gas and air, but it's really the volume of gas and air that's in the tank, that gas or air rather, I should say, that's in the tank that will control the surges. But yes, in a general sense, a bigger tank is better, and the bigger it gets, the more effective it is at controlling surges. And obviously, you don't want to have a surge tank that is much larger than you need. You just want it to be big enough to control the surges to acceptable levels, and then beyond that, you don't need to make the surge tank any larger unless you're using it for some other purpose, like a hydropneumatic tank. But if it's just purely for surge purposes, then it shouldn't be any larger than is absolutely necessary.
Thank you.
David, this has been very educational. I really enjoyed seeing your presentation. I really appreciate it.
No problem. It's my pleasure, Michael.
Yep. If no further questions, we can go ahead and conclude this. And I would like to thank you again, David. I really got so much off of this, but this is a very vast field of knowledge, and it takes some time to grasp all the activities of this. But I really thank you for your time.
No problem at all. Thank you very much to AZ Water for giving me this opportunity to talk with everybody about surge control and its application in the pumped systems. I've enjoyed it. And if anybody has any questions after the presentation, they can contact me at the email or telephone address on the screen.
Thank you, David.
Thanks very much, Michael, and everybody for attending. Bye-bye.